Hello friends, myself Tejaswini Aage. I am from Yashwantrao Chauhan Art and Science College, Mangalore district, Washing. I am student of BSc second year. I can give a short presentation on the topic of group of homomorphism and isomorphism. Let us know about some content. Homomorphism and isomorphism. Second is some important definitions. Third is example. Fourth is theorem, and fifth is references. Now first is homomorphism and isomorphism. Definition of homomorphism and isomorphism. Homomorphism. Let G, comma star and G dash, comma dot be a two groups. A function or mapping f from G tends to G dash is called as homomorphism if f of x star y is equals to f of x into f of y for all x comma y belongs to G. Thus, if f is a homomorphism from G to G dash, then f preserves the compositions in G and G dash. Now, isomorphism. If a homomorphism of f from G tends to G dash is a bijection, that is a one-one and onto function, then f is called as isomorphism between G and G dash. And we write G is equivalent to G dash. Second is some important definitions. First, monomorphism, epimorphism, automorphism, and last is endomorphism. Now first, monomorphism. A function f is called as monomorphism if f is a injection, that is a one-one function. Second is epimorphism. A function f is called as epimorphism if f is an surjection, that is a onto function. Third is automorphism, and isomorphism from G onto itself is called as automorphism. And last is a endomorphism. Of a homomorphism of a group G into itself is an endomorphism. Thus, a homomorphism f from G tends to G is a endomorphism. Now, let us know some examples. First example: consider the two groups R plus the adjective group of real number and R0, comma dot the multiplication group of non-zero real numbers. Define a mapping f from R tends to R0 by f of x is equals to e raised to power x belongs to, for all x belongs to R, show that f is a homomorphism. The solution: define a mapping f from R tends to R0 by f of x is equals to e raised to power x belongs to for all x belongs to R. For to show that f is a homomorphism, let x comma y belongs to R. Now by definition, f of x plus y is equals to e raised to the power x plus y for all x comma y belongs to R is equals to e raised to power x into e raised to power y. This equals to f of x into f of y. Hence f is a homomorphism. Now second example is let R be the group of all real numbers under the addition and R plus be the group of all positive real numbers under the multiplications. Show that the mapping f from R tends to R plus defined by f of x is equals to 2 raised to power x for all x belongs to R is in the isomorphism. Solution: define a mapping f from R tends to R plus by f of x is equals to 2 raised to power x for all x belongs to R. To show the f is an isomorphism, first to show that f is a homomorphism, let x comma y belongs to R. Now by definition we have f of x plus y is equals to 2 raised to power x plus y for all x belongs to R. This implies that 2 raised to power x into 2 raised to power y. This implies f of x into f of y. Hence f is a homomorphism. Next, to show that f is a bijection, that is a one-one and onto function for any x comma y belongs to R, let f of x is equals to f of y. This implies that 2 raised to the power x is equals to 2 raised to power y. This implies x is equals to y. Therefore, f is a bijection, that is a one-one and onto function. Next, take any a belongs to R, then log a to the base 2 it belongs to R, and f of log a to the base 2 is equals to 2 log a to the base 2 is equals to a. Every element in R plus has a pre-image in R, that is f is onto. Hence f is a bijection, that is a one-one and onto function. Hence, F is a homomorphism and a bijection. Therefore, F is isomorphism. Then another example is the same as like second example. Let R be a group of all real numbers under the additions and R plus be a group of all positive numbers under the multiplication. Show that the mapping F from R tends to R plus defined by f of x is equals to log x to the base 10 for all x belongs to R is an isomorphism. Now, fourth is theorem. Consider a group G star and G dash dot with the identity elements E and E dash respectively. If f from G tends to G dash is a group of homogeneous homomorphism, then prove that f of E is equals to E dash. Second is f of x inverse is equals to f of x inverse bracket inverse. Third is if H1 is subgroup of G and H2 is a f of H1, then H2 is a subgroup of G dash. And fourth is if F is an isomorphism from G and up onto G dash, then F inverse is an isomorphism from G onto G dash. Then proof. Let F be a homomorphism of a group G into G dash. Then assume X belongs to G. Then first is f of x inverse. Sorry, f of x into E dash is equals to f of x because E dash is an identity in G dash is equals to f of x into E because x is equals to x into E is equals to f of x into f of E. Since f be a homomorphism, this implies E dash is equals to f of E by a cancellation rule. Second is E dash is equals to f of E is equals to f of x into x inverse is equals to f of x into f of x inverse for all x belongs to G. This implies that f of x inverse is equals to f of x bracket inverse is equals to inverse of f of x in G dash. Third is H2 is equals to f of H1 is the image of H1 under a f that is the subject of G dash. Let x and y belongs to H2. Then x is equals to f of a and y is equals to f of b for some a comma b belongs to H1. Since H1 is a subgroup of G dash, we have a star b inverse belongs to H1. Consequently, we can say that x comma y inverse is equals x into y inverse is equals to f of a into f of b bracket inverse is equals to f of a into f of b inverse is equals to f of a star b inverse. This implies that f of a star b inverse belongs to f of h1 is equals to h2. Hence h2 is a subgroup of G dash. Now, fourth is since f from G tends to G dash is an isomorphism, then f is a bijection. Therefore, f inverse is from G dash tends to G exists and is a bijection. Let x and y belongs to G dash, then x and y belongs to G dash then x into y belongs to G dash and there exists a comma b belongs to G such that x is equals to f of a and y is equals to f of b. Therefore, f of a inverse is equals to f of a f inverse of x into y is equals to f inverse of a into f of b. This equals to f inverse of a into f of b. This implies that f inverse of f of a into b now by cancellation rule f inverse and f become cancelled is equals to a into b is equals to f inverse of a into f inverse of b. This show that f inverse from G dash tends to G is an homomorphism as well. Therefore, f inverse is an isomorphism. Hence, proved this theorem. Now, some references which is used to make this presentation. And thank you.